Good morning, everyone. Today I will present our work, a novel analytic approach called SeNA for uncovering social and spatial insights during collaborative learning environment. We humans are social beings. Being able to connect and work with others are essential for developing 21st century skills, such social encounters are also vital for our mental well-being. There is also empirical evidence connecting social interactions with academic performance and progression. But how do social interactions occur? They don't just occur in random. One of the essential concepts for investigating the occurrence of social interaction is homophily. This is a sociological construct that describes the tendency of individuals to interact with others who share similar characteristics. For example, the entire lab conference is to facilitate homophilic interaction among people who are interested in learning analytics. However, within this large community, we can also observe heterogeneous interactions between researchers in collaborative learning and self-regulated learning. These different types of homophilic interaction can contain meaningful educational insights regarding whether students are adhering to teachers' grouping strategies, understanding the relationship between students' social capital and their academic performance, and identify potential inequality that might exist in our educational systems. However, capturing these interactions are challenging, especially with traditional data collection methods, such as survey, interview, and direct observation. These methods can be intrusive, labor-intensive, and susceptible to memory and observer bias. The recent advancement in multimodal learning analytics has offered many alternative ways to capture individuals' physical and physiological data within co-located learning settings, of which wearable tracking system has shown evident relevance for unpacking the social and spatial aspect of collaborative learning. Potential instances of social interactions can be identified from X and Y positioning data using an including distance modeling approach. The most predominant approach to analyze these identified social interactions is through social network analysis. However, social network analysis often lacks the consideration about the temporal aspect of social interactions, which can contain valuable insights regarding the changes and the evolution of one's social behaviors. Additionally, conducting statistical comparison among different homophilic interactions and among different groups is also difficult with this approach. A more recent network analysis approach, epistemic network analysis, take into account the temporal dynamics within the data and self-embedded with the function to conduct statistical comparisons. Therefore, the current study proposed a novel approach that infuses social network analysis with epistemic network analysis to enable more variety ways of analyzing homophilic interactions. We call this approach SeNA, Social-epistemic Network Analysis. I know, super creative, right? This approach contains 4 different stages. I will go through them, the details of each stage using an example. This example is built up on top of a position dataset that we collect in open plan primary school, where 98 students study in this open learning space that aim to maximize student connectedness. The data contain the X and Y positioning coordinates of 98 students across 38 math and 23 reading sessions. We model social interactions from the raw data by calculating the Euclidean distance among every possible pair of students. A potential interaction was only recorded when the proximity among 2 students are within 1 meter threshold and lasted for more than 10 consecutive seconds. This criteria is used to reduce the likelihood of misidentifying unintended collocation from proximity as meaningful interaction. After the social interaction was identified, we infuse each student with their demographic data, such as their prior attainment in math and reading, the home group they were assigned to at the start of the semester, and their self-identifying gender. Using these social interactions, we constructed an undirected social network where a node is a student or teacher who can be connected to others through an edge. The weight of this edge is the duration of interaction among two nodes. This is how the social network would look like when infused each node with their corresponding attributes, such as prior attainment in reading. And this is another example with gender as the node attribute. So using these identified social interactions, we can then use epistemic network analysis to account for the temporal changes in homophilic interaction. Here is an example of students having homogeneous interaction for the duration of T1 and T2, but change to heterogeneous interaction at T3. We consider the temporal changes in 4 types of homophilic interactions, including gender, prior academic in reading and math, which we use for student grouping in these 2 subjects. Home group homophilic interactions, which was also used for student grouping for other subjects. These homophilic interactions were compared among 3 different comparison groups, including comparing low and high progressing students in reading and math, and comparing socially disengaging and engaging students. Let's first look at what additional insights SeNA can offer compared to social network analysis alone for low and high progressing students. Based on the findings of social network analysis, there is at most a weak academic homophily in math, and there is no statistical significant differences between low and high progressing students regarding all 3 types of homophily in math and reading. SeNA, on the other hand, reviews some additional insights regarding the behavioral differences. After we accounting for the temporal dynamics of these interactions, we identified that in reading, low progressing students interact predominantly with students from different academic groups, whereas high progressing students mainly focused on interacting with others from the same academic groups. On the other hand, in math, these differences were more complicated, as shown by the triadic connections for both low and high performing students. These findings are actually in line with the differences in instructional design, where in reading, the behavioral differences manifest primarily from academic homophily because the mandatory collaborative reading activity adopt an academic-based grouping strategy. Students' homophily differences were more diverse in math as the subject was designed with a higher level of learner autonomy. Based on this finding, we have reviewed 2 insights. Comparing social network analysis metrics separately for each type of homophily was insufficient to review the behavioral differences between low and high progressing students, potentially due to the weak overall homophily of the classroom network. And these differences were only made visible after applying SeNA to infuse social-spatial analytics with temporal insight. Similar findings were also identified in the second research question. We categorize students based on the change in their social participation level over time. As you can see, cluster 2 students in math and cluster 4 students in reading clearly demonstrate a declined social participation level over time, and thus we categorize them as socially disengaging. In math, the results from social network analysis attributed such differences to their academic homophily, with socially engaging students demonstrating high tendency of academic homophilic interaction. We didn't find any differences in reading across all 3 types of homophily using social network analysis. However, from the results of SeNA, these differences were quite obvious in reading. We found that socially disengaging students interact primarily with students from the same home group, whereas socially engaging students interact mainly with students from different home groups. In math, the differences is more complex. After account for the temporal dynamics among different homophilic interactions, the homophily of socially disengaging students was strongly characterized by the triadic connections between gender heterogeneous, home and academic homogeneous interactions, and the dyadic connections between academic heterogeneous and gender homogeneous interactions. In comparison, socially engaging students' homophily was strongly characterized by the dyadic connections between academic and gender homogeneous, as well as between academic homogeneous and home heterogeneous. Ooh, very complex, right? So what does this all mean? Well, these findings suggest that socially disengaging students tend to interact mostly with other students from the same home group, which could potentially indicate their less diversified social strategies. Also, students from the same home group were more likely to be friends, as they were grouped together for the most of their time other than reading and math. So potential friendship issue could be an important point of investigation for teachers to understand the reason behind their declined social participation level. Once again, SeNA reviewed additional insights compared to social network analysis. Instead of bragging about our novel approach, I want to stress the importance of considering the temporality in learning analytics research. Whether you infuse your data with temporal information can have substantial impact on your final research finding. Another thing I want to touch on is that SeNA and other social-spatial learning analytics approach could potentially provide the insights we need to support teachers' classroom orchestration, such as identify and support socially at-risk students and pinpoint the potential causes behind these issues. There are two limitations with our approach. First, proximity-based identification is at most an estimation of social interactions. Even though we apply the two criteria to make this estimation potentially more reliable, it could still misclassify unintended co-location as meaningful social interaction, especially in newly formed classrooms where students are based practically strangers to each other. Another limitation is we used a binary classification for the illustration, but in the future we should definitely be more inclusive and considering more categories for attributes such as gender. There are also several ethical implications of our studies. There is a dilemma between using anonymized data and having personalized support. How is that possible? Right? So if we want to personalize the amount of support we can provide to students or to teachers, we might need to use identifiable data. This brings us to our second implications. If we're going to use identifiable data, we need to ensure the privacy and security around students' demographic data and related information. In the current study, we only use teachers' grouping strategy and gender information. But what if future study use student socioeconomic status, use their gender preference? These are more sensitive information that we need to be aware of. There's also a concern regarding labeling students. Labeling students as socially disengaging, that could potentially have negative effects on teachers as well as students. Thank you for your time and attention. That's the end of my presentation. Thank you.